to warm up a little bit the outside, but apply to electroweak baryogenesis.
Yeah, supersymmetric theories. Okay, thank you for the introduction. Yeah. So that's the topic. Okay, another thing title written in the program is the reassessing the window for electroweak baryogenesis in general. So I'll start with the introduction what the electroweak baryogenesis is. So we see mostly matter around us in no antimatter. We don't know why that happens. And the electroweak baryogenesis is one of the possible ways to explain the asymmetry between matter and antimatter. And the crucial component of the electroweak baryogenesis is the first order electroweak phase transition. If long time ago there was a first order transition from the phase with the zero Higgs wave or small Higgs wave to the phase with large Higgs wave, which proceeded through the bubble nucleation, you would have a situation when we have expanding bubble walls with some large Higgs wave inside and zero or small Higgs wave outside. So that's the phase transition. If there is certain sources of CP violation associated with these bubble walls, then while passing through the plasma of particles, they can create some spatial separation of particles and antiparticles. So there can be more antiparticles in front of the wall, more particles behind. And because of that, because of very small Higgs wave, there will be certain standard model processes, electroweak sphalerons, which can dilute the excess of antiparticles. So as a result, you have a net asymmetry. You have more baryons than antibaryons, because here there is no sphalerons. They are not active when the Higgs field has a large value. So that's the critical component of the electroweak baryogenesis. And that's what is the most important part for the rest of the talk. So we look at this diagram of the H over T, which we are interested in as a function of temperature. The standard model actually tells us that it smoothly goes to 0. Around 100 GeV, it becomes 0, and that happens smoothly. It's just a second order transition. It's not the first order transition with bubbles that we need. It's just a more or less homogeneous change of the wave in the entire universe. So if you want to do electroweak baryogenesis, you need to add some new physics to change this. And this new physics has to kick in somewhere in this range of temperatures. Let's say here roughly, such that you have a jump. So that's the first order transition. On top of that, you typically need some extra sources of CP violation to get this asymmetry in front of and behind the wall. So that's new physics. And it has to be light. So it's linked to this 100 GeV scale. So this is very nice because this physics can be testable in collider experiments. It can have imprints in the electron medium measurements. The problem is that as of today, the bounds are actually very tight. So what you can need, for instance, what can make this happen is, for instance, light stops. In an SSM, you can need a light dilaton. In composite Higgs models or radio in RS models, you can need some light superpartners of electroweak gauge bosons. And some of them are already completely excluded, like light stops, which are needed for the first order phase transition in MSSM, just already excluded. light dilaton is under severe pressure. So there was an idea to kind of change the situation. Keep the main ingredients of electroweak baryogenesis, but get rid of these bounds by changing the thermal history of Higgs field. So the idea by a number of authors was to change in some way this behavior such that the Higgs field stays large till some very high temperature, let's say 100 T. In this case, all this new physics that you need for the first order transition, for the CP violation, you can just put it there at 100 TeV, for example. And in this way, it just escapes all the experimental constraints. The scenario, becomes actually very hard to test. In a way, it just loses that original advantage of the electroweak baryogenesis as a possibility, but well, if it is a possibility, then it should be considered. So that's the general idea, and I'll just briefly review how this can be done.
So can you remind me again, what do you have to give up to go to high temperatures?
Sorry?
What do you have to give up, so to speak, to go to high temperatures?
You mean this?
Yeah.
So I'll just discuss it now. So the problem why there was this drop here is because, well, not the problem, but well, the feature of the Standard Model is that the Higgs couples to the Standard Model particles which are in plasma at that temperature. For example, you have these interactions with the top quark, and that induces the loop correction, thermal correction to the Higgs potential. This thermal correction of the size so it is strictly positive. It's a positive thermal mass induced by the top quark, which is in the plasma and which interacts with the Higgs field and reacts on it like this. So clearly at some high temperature, this positive correction will just dominate over the negative quadratic term in the Higgs potential and give you this smooth transition. And this is kind of expected. So what we are computing here, when we're trying to find the minimum of the Higgs field high temperature, we're computing the free energy. So, which depends on just the usual zero temperature potential and the entropy, which is something like so we need to maximize the entropy, so that's where the minimum is. So we need to minimize the mass. The mass of the top is minimized for zero Higgs wave. So the thermal correction searches for the place where the mass is zero or small, and this is the place where the Higgs wave is zero. So that's why this correction. And this also tells you what to do if you want to change that, if you want to go from this to that. You need to introduce some particles whose mass dependence on the Higgs wave will be different. Will not have a minimum at zero Higgs wave, but at some large Higgs wave. And so in principle, the first models of this kind were introduced like in 1974 by Weinberg, but are related to the electroweak symmetry. And for the electroweak symmetry, it was done just like 5 years ago. And the idea is simple. We need to write down some extra model with some extra states which have this unusual dependence on the Higgs wave. So for instance, you add some new scalars. Let's say chi, which have bare mass term and the negative correction to the mass, which comes from the interactions with the Higgs. So that clearly does the job. You have the mass, which is minimized at Higgs being this over that, so large Higgs value, and you produce a thermal correction or something like that, which has a minimum at large Higgs value. You can also do this with fermions. This is what we did with the Geraldine. The situation with new fermions is slightly different because the simplest operator allowing to couple a new singlet fermions with the Higgs is of this form. Well, I said the fermion is called psi, rest of their mass, and the coupling has to be a dimension 5 operator. So there is a cutoff which leads to certain constraints in the theory at the end. So it looks simple. There is the main kind of big disadvantage of all that is you cannot have just one fermion or just one extra scalar. You need many. Why? So this term here is the negative cross-quartic correction. If it is too large, overall the potential will get a runaway direction. So it will be unbounded from below. So the potential for the Higgs and the chi. So for this not to happen, the quartic, this cross-quartic, has to be less than, okay, up to some order 1 factors, the Higgs quartic times the quartic coupling of these new states. This one is fixed, the Higgs quartic, of course. This one, in principle, you can choose it large, but it should stay perturbative. And the bound will be, well, 6 over n. On the other hand, this thing is something that gives us the negative thermal correction, which has to be greater than the correction induced by the top. So it has to be, okay, some order 1 factor, this, okay, 1/8, whatever. And over n, over n squared. Why over n squared? Because this correction, when I compare thermal corrections, the thermal correction from here is actually enhanced by n. So let me write it down. Well, so there's some sequence of inequalities. In the end, you see that n has to be greater than something, and what it is eventually is, well, it depends how close you want, how well you want to be under control, and keep this non-perturbative effects under control. And okay, the numbers is like hundreds, thousands, etc. So you need a lot of new scalars. For the fermion, the situation is a bit different because, okay, there's no issue of the potential, these are just fermions, but there are higher order interactions. And what the problem is now is that there will be 2 loop effects. The one loop effect that you want to have is this. So this is Higgs, this is no fermion. This will give you the negative thermal correction to the Higgs mass of the size 2. And so like this, there is a loop. I mean, the counting the multiplicities is just the same as when you compute the 0 temperature loop integrals. So there's a closed fermionic loop. So there's a factor of n for the number of fermions which run in the loop. But there will be higher loop effects, which will grow with temperature because there is this explicit cutoff present in the theory. there will be a diagram like this, going like nt squared over lambda squared. And so that tells you that, okay, at some point, at some point the tube will blow up. And comparing the two, you see that the maximal temperature scales the square root of n. So that requires you to have large n in the end. So let's say you take 1 TeV for the temperature where this whole thing is under control. Let's say 1 TeV. Then you need 10 new fermions to add. Well, so that's what it is. Whether you like it or not, you need new states. You can work a bit on that. Let's say in the two Higgs doublet models, you can use the second Higgs to break the electroweak symmetry. The second Higgs can be inert. It will not have this coupling at the top, but it will have the couplings to other standard model particles, for sure the gauge bosons. So there will be some positive thermal correction used by the standard model, which you'll have to overcome, but it will be lower than that. In the end, you can win a factor of 5 in the new states. So let's say not 100 but 20, not 10 but 2. Yeah, so that's it. So that's kind of the introduction or the answer to the question of how this can be done, if that answers, I hope. Now, so this is known. The question I like to ask is how reliable is this extrapolation to 100 TeV, where all the baryogenesis physics would get decoupled. In practice, okay, so this of course assumes that the standard model stays unchanged from 0 temperature to 100 TeV temperature. In practice, if you care, for instance, the hierarchy problem, necessarily the Higgs sector will change. Let's say, like the most obvious case is the composite Higgs. In the composite Higgs, when you go to temperatures, say, order TeV, this new strong composite dynamics just deconfines. You don't have the Higgs anymore, so there's just no point of speaking about the Higgs level at high temperature. There is no electroweak symmetry breaking induced by this Higgs anymore at all. So in that sort of scenarios, what you can have at most is that maybe you go to 1 TeV. That still changes the story. You can still remove this new physics to 1 TeV, which is important and can dramatically change the signatures, but not to the extent that they disappear completely. You will still be able to test them. Another hierarchy problem motivated case is supersymmetry. Okay, this one doesn't seem to have obviously this problem because the Higgs stays there as an elementary state up to Planck potentially. However, it turns out that there are problems as well. So this is what I will discuss. So the high temperature breaking of symmetries in supersymmetric context was studied quite some time ago for different purposes. For instance, to avoid formation of monopoles or domain walls if the gut symmetry gets restored at high temperature. So people were looking how to prevent the restoration of the gut or other symmetries. And people came to the conclusion that there are problems. Okay, so the first set of problems by Mangano and Haber, they found out that in renormalizable supersymmetric theories, you cannot get symmetry breaking at high temperature. And this can be derived easily just using two facts, two simple equations. First of all, the general form of thermal corrections induced by some particles is like that. So there's the thermal correction. These masses are functions of your scalar fields of your theory, so that gives you the potential to those scalar fields. And these are masses of scalars, fermions, and spin-1 fields. And this assumes that, so this is high temperature expansion for the thermal correction, so it assumes that all the masses are smaller than the temperature. And all the states are thermalized, so they are in thermal equilibrium. And the second crucial equation is, the property of softly broken supersymmetric theories is that the supertrace, which is not a function of fields. So this combination of masses is not a function of fields, and this is, for example, the property which allows the Higgs mass to be insensitive to the n-Planck or whatever higher order quantum effects, is because this is precisely the quantity which controls the quadratic divergence to the Higgs mass. And it is not a function of the Higgs field in the supersymmetric extensions of the standard model, which makes the corrections vanish. Just using these two equations, first of all, you see that the fermionic contribution enters with different coefficient in the thermal and in this part. So you can use this equation to remove this and this from here. And what you will get is that the thermal correction is just proportional to the fermionic mass squared. The problem is that this is clearly a positive definite quantity. Zero. Maybe zero. Let me write it somewhere higher. So this this is dimension 2. So in your normalizable theories, it can have at least 2 powers of the fields. So this thing is something like some constant plus some other constant, phi plus third constant, phi squared. So phi is the scalar. Let's do the Higgs. So this is positive or 0, so this coefficient has to be positive or 0. That means that this correction gives a positive mass. So there will be plus Higgs squared times temperature. So if you're normalizable, you get positive correction to the Higgs mass. So that's it. That's pretty okay. Just another comment. So this term C3. You can only have C2. You can only have it if you have some other field which transforms as a Higgs doublet. So you can write down, let's say, H, some C2 coefficient.
What's the assumption about supersymmetry breaking in order with the supertrace formula? Because I know that it's exactly 0 if you have just spontaneous breaking, but then if you do it in the hidden sector, then the sum rule is not 0, but I don't know this relation that it's independent of the fields. So does it depend on whether you have like gauge mediation or gravity mediation or?
To my poor knowledge, I would say no, but you should know better, I guess. So, sorry, that's my textbook knowledge about supersymmetry. So in principle, you can have several fields. In this case, you can have some, let's say, negative correction here, such that they conspire that overall, at most, you can have some flat direction between H and H tilde, so that this is 0. But I don't really know how this can be useful. So maybe there is a way to use it, but yeah, I don't know. So I will not consider this. Just single Higgs story. So that's the conclusion. Just with the requiring renormalizability, the high T expansion, and soft breaking, you get this. Now the obvious thing, okay, let's go to non-renormalizable theories. In this case, we can have something like this. The next term, let's put some cutoff here. Now it is this guy who has to be positive in order for this to be positive. This instead can now have a negative coefficient. So you can have a negative correction to the Higgs mass. At this point, for example, just you have a fermion with the mass. I already wrote it down for the, okay, it was just here. So the Lagrangian of this sort. So this is precisely what we were doing for symmetry breaking with fermions. We were using this dimension 5 operator. And now if you write down a supersymmetric theory where you have fermions with this mass, you can have a negative term here. And the simplest case, so this was first proposed by Valley and collaborators. And well, they wrote down a set of models, but the simplest is like that. So something like, okay, I omit all the order 1 factors. So this is not the Higgs, just some scalar field phi, which has a symmetry. It's phi to minus phi. And we can check how it behaves at high temperature, this symmetry. So what you see, okay, you will see that you will get the fermions with the mass of this sort. Or you can also just compute the scalar potential. And well, the scalar potential will have a mass term. Plus it will have, okay, I'll put a minus plus, let's do it like this. Again, I omit all the order 1 factors. And many other details like indices. Anyway, so here, no, again minus. So you get negative quartic term. So at high temperature, this gives you something like mu over lambda times temperature squared times phi squared minus negative mass from the scalars. You also get the negative mass from the fermions counterpart. And if this is greater than that, you get symmetry no restoration. Guess, can anyone see what's happening here? Yeah. So for this to work, you need that the T squared is greater than mu times lambda. So when temperature raises above some threshold, you get this. Of course, the temperature has to be below the cutoff because the theory gets not applicable anymore. However, it was later noted by Sinanovic and collaborators that this is not the whole story. In fact, there is an extra term here, necessarily positive. Just because it comes from the square of this last part, and it's required to be here just by supersymmetry. And also it can be seen to be required here because overall the potential which comes from superpotential is just by definition positively definite. You cannot just have higher order term which has a negative coefficient. There has to be something next which is positive. And this guy gives you two correction. So you need to contract the phi field twice, and you get something like T4 over lambda squared. And if you want this guy, so this is positive. So your negative, if you want to have symmetry and restoration, has to exceed both this and that. So what you see, so for this to be less than that, you need the opposite condition actually, which is not compatible. So they concluded that there is kind of a non-go for SNR in supersymmetry, even if you go to non-renormalizable theories. But in fact, this sort of higher order effect is something that we already dealt with in the model with fermions only. I remind you that in the model with fermions, which is actually just a subsector of this model, the model with fermions, I mentioned that we have a two-loop correction, where this is new fermions, this is the fix, which goes like n p squared over lambda squared t squared, this correction to mass. And I said that by taking large n, you can actually make this subdominant compared to the leading correction. And you can do precisely the same thing here. So you need to extend this model to a model which has some UN symmetry. Say So we want to have UN symmetry, we need to have two fields to write down the superpotential. So let's say phi 1 and phi 2. And those phi 1 and phi 2, they are okay. And fundamental and fundamental of some UN. So now, if you just compute the potential which comes out of this, you see that the potential, okay, it's the zero temperature terms are unchanged. The quartic terms have this form. And the quartic term has this form, 1 over lambda squared, just like this, phi 1, It is crucial that this term is not, for instance, that y. So now let's just, the general expressions for the thermal corrections will have the same parametric dependence, but there will be some extra factors of n here and there. Okay, first of all, so now in this case, that's a mixing. It's not a correction to the mass, it's a correction to the mixing. But it's still fine because if you have a very large mixing, that one of the mass eigenstates becomes negative. So that shouldn't confuse you. So you still just need to compare coefficients in front of here, in front of this term, and in front of this term. So I can close a thermal loop here that gives me t squared, and it's just an and there will be a multiplicity n because it's just a contraction of indices here. Okay, let's even do plus, doesn't matter. Here, because of the shape, because of the index structure of the potential, I can only do this sort of contractions. So if you see, I mean, if you follow the flow of indices is just one line. So there's just one factor of n in the end. So what you see is that there's the same factor of n which appeared in these thermal corrections. So in order for these to be less than that, the condition is just the same. But in order for these to be greater than that, the condition has changed, and we gained a factor of n here. So now actually choosing large n, you can get some space to, where you have symmetry breaking. So that's, okay, it's kind of general conclusion for this part. And now I'll switch to the actually electroweak symmetry breaking, so if you have general questions. Okay, so that's the story. Let me think. Should I say something more on that? That's it. So now we go back from this toy model to actually electroweak symmetry. The Higgs unfortunately cannot be this phi field because for the Higgs it's just a doublet. So n is just 2, it's not really a lot to allow for any interesting range of temperatures where this works. So one actually needs to write down a model where we have the Higgs is, as usual, 2 and also some extra fields, phi. So the superpotential has to include this sort of, so again, phi 1, phi 2, coupled to h up, h down. This will induce a negative correction to the Higgs mass. So the potential eventually will have a term, something over lambda phi I squared h up, h down. So you can introduce again the off-diagonal term for the Higgses by closing the thermal loops here. So you can destabilize one of the Higgs, both Higgses, or one of the mass eigenstates. Anyways, and so concretely the effects will look like, so you will have this Higgs phi interaction, which gives you a negative correction of the size of this mu over lambda t squared. So that's correction to the Higgs interaction. Scalars. There will be the same correction from the fermionic counterparts. So these are fermionic partners of those scalars. They will also induce similar correction with a slightly different numerical coefficient. This diagram, again, over lambda t squared. And the higher order effects can be suppressed if you choose large n. Okay, so that's the model for the breaking of the electroweak symmetry at high temperature. Okay, there. Which, okay, we already checked numerically. I don't want to show you the plots because, well, it works. Nothing interesting to see. The next steps is to show that you can actually have, so that achieves this part. Temperature breaking, then you can add some new physics to get the first order phase transition, to get some CP violation, which can be at higher temperatures, at higher masses. The main conclusion that I just wanted to deliver to you is that this bright picture of having, like removing the electroweak baryogenesis to inaccessible mass scales, well, it looks nice, but in practice, when you try to combine it with the theories based on natural mass considerations, it doesn't really work. if you want to go to 100 TeV, you would need n's. So n grows as a temperature grows as a square root of n. So here you would need like tens and hundreds of thousands of new fermions or new states to get to these temperatures because of those non-renormalizable effects. So realistically, if you are okay with having a few, let's say up to 10 new states, even in supersymmetric theories, same way as in composite Higgs, you'll only be able to move somewhere to the TeV-ish range, where you can indeed escape the current bounds, but eventually you will be tested maybe in the next generation experiments. So, which I think is a positive thing. Yeah. So yeah, that's it. Yes. The point is that so the thermal effect which they induce has to start being important already around 100 TeV. So if I add some doublets or something, they will be excluded by collider searches. So you should should go with singlets in this case. Yes.
Once you introduce some non-renormalizable operator to some fairly low scale, don't you get just simple direct contributions to the Higgs potential, like from operators just involving Higgs?
Sorry?
Say Higgs to the 6 corrections directly from non-renormalizable operators, like I don't know, HUHD squared.
You'll have some corrections.
And they don't change the order of the phase transition. They can, people obviously fake with that, but once you already assume that there's a low scale lambda.
Well, it's not really low scale. It's several TeVs.
Okay, so I'm not sure how low you can.
So
I know that people, they say.
But okay, so yeah, the non-renormalizable interactions are here, but you cannot, let's say in this case, if I have, so what happens? Okay, but finish.
No,
because I think I interrupted.
Maybe a stupid question, but so you can certainly just by adding non-renormalizable interaction to the Higgs potential change the potential, no?
Yeah.
Like fight with the Higgs to the 6 and so on, no?
Yeah.
In supersymmetry, I guess it will be HUHD squared.
Yes. So first of all, for sure, the phase, you will not be able to get phase transition somewhere here. It will have to happen at this temperature because of the thermal effect of the stellar model particles. They are here. I erased it. Effect of the top. It will make it fall down here.
Right, that's true.
So
But you don't need, sorry, yeah.
No, just to understand your question and its answer. So it's enough just to keep the H over T to guarantee the strong first order.
Yes.
Yes, you need, so precisely the boundary is around 1.
Right. So whatever happens above 1 TeV, I guess, not doesn't change the order of the transition around 1 system, which is what you really.
Yes, I really want to remove the phase transition to high temperature. I really want the H over T to be large.
Right.
If you just add higher dimensional operators, so what's important for this guy is the interactions here between H equals 246, and here the top brings you to 0 Higgs value eventually. So if you modify the Higgs potential somewhere far away, it doesn't really change much. It can get it can give you some thermal effects, but they will be kind of small because, they will be T squared over lambda suppressed if you get some extra terms with the Higgs potential. So I don't see how that can make you stay at a large
Okay, so if you
Higgs field
insist you
values.
want a higher scale, but I mean you don't, in that case you don't even need a high scale.
What?
In that case you don't even need a high scale in a sense, no?
Yeah, but you just have a standard electroweak baryogenesis at low scale, so you'll have some new interactions of the Higgs field, some CP-violating interactions which are associated to this scale. So you will get constraints from everywhere, from DMs.
Yeah, I'm not an expert at all, but I remember some talks where people said you can change the Higgs potential at low, at least in a non-supersymmetric setting, you can change the Higgs potential quite a lot without running into many other constraints from colliders and stuff.
Yeah, so, but what do you get in this case? Okay, so you change the potential, you still have the phase transition at the same temperature. I'm sure you cannot
Okay,
get...
you're right, it is still a low temperature phase transition.
So you still have all this new physics, low temperature, and if you want to have sizable CP violation, for example, at those temperatures, those high dimensional operators that you introduce, they cannot be suppressed by very high scales. Because otherwise you will not get CP violation at this temperature. So, yeah, I don't see... Well, let's just, I don't know, just give you an example. Okay, composite Higgs. Okay, it has all high dimensional operators you want. What happens in the minimal models is that, let's say there is a confinement phase transition. Confinement phase transition of this new strong dynamics, which gives you the Higgs compositeness. So the electroweak phase transition can happen at the same time. So the Higgs condenses together with the confinement phase transition, it appears and breaks the electroweak symmetry. So the electroweak symmetry breaking happens together with the confinement phase transition. So because of this feature, this confinement phase transition should be such that the temperatures of the transition, their heat temperature after the transition is below roughly 130 GeV. So that puts you like constraints on the models, on the mass of the dilaton, on various parameters. Now you do this, and you see that now their heat temperatures can be 1 TeV. So you now open up the parameter space of the model. So, just an example.